Okay, we're going to talk about periodic trends today, and this is the behavior of elements on your periodic table, and taking into account that repeating behavior, those repeating chemical and physical properties we talked about earlier. When you're talking about periodic trends, there's a few things you need to keep in mind. Well, before we do that, let's review some parts of the periodic table. To begin with, as you go across the periodic table, we call those the periods. The horizontal rows are called periods. Your columns, your vertical columns up and down, those are called groups or families. Groups or families. So periods are across, groups and families are up and down. And to remind you, the periodic law says that when elements are arranged in order of increasing atomic number, in other words, when they're arranged in order of increasing number of protons, like our periodic table is, you can see a periodic repetition of physical and chemical properties. You'll see a pattern that repeats every so often, these physical and chemical properties. That's called your periodic law, and that periodic law is what helps us arrange the periodic table, how it's arranged. And it gives us a lot of information about the individual elements. Okay, again, some more vocabulary to remember. Representative elements are the group A elements, the tall parts of the periodic table, the S's and the P's on the periodic table. We call those the representative elements or the group A elements. Those are the elements that are predictable, that behave in a predictable fashion. Your D's, F's, those are called your group B elements. Representative elements are group A, main group elements. Okay, and our periodic table can be divided into three groups. It can be divided into metals. That's the part on your periodic table that is colored mostly yellow. The majority of your periodic table is metals. Top right-hand corner of your periodic table are where your non-metals reside. There's a handful of those, but the biggest group is your metals. And then you have your metalloids, and those are the elements that are right along that stair step on the periodic table that's marked with a dark black line. And those are called your metalloids, and those are that transition between your metals and your non-metals. This is where your semiconductors live. Before we get into our periodic trends, there are three factors that you need to take into consideration when you're considering all of these periodic trends. And if you keep these three factors in your mind when you're thinking about the periodic trends, they make a lot more sense. So the first one that we're going to discuss is your nuclear charge. Your nuclear charge. Okay, this is something that is most relevant as you're moving across a period. So across the periodic table, across a horizontal row, your nuclear charge is going to dominate in terms of the influence on these periodic trends. So whenever a proton is added to a nucleus, okay, so you go from one proton to two, from hydrogen to helium, you're creating a stronger nuclear magnet because you've got a stronger positive charge pulling on those electrons even more. So as you go across the periodic table, you are adding a stronger pull from the nucleus, pulling those electrons in. You can kind of think of these protons, the positive part of your nucleus, the protons, as the parents who are trying to control the children, the electrons. The electrons want to get out, get as far away as possible. The protons want to keep them in. Protons are pulling them in. There's a nuclear pull, a magnet pulling electrons in more. So let's look at lithium versus fluorine. Lithium and fluorine are on in the same period, the same energy level. That's in the second energy level, the second period of the periodic table. So in other words, they have two energy levels. Lithium has 3 total protons, while fluorine has 9 protons. Okay, so you have, for lithium, you have 3 protons that are pulling in on 1 electron. 3 protons pulling in on 1 electron, as opposed to fluorine. Fluorine has 9 protons that are pulling in on, let's say, this 1 electron on the outside. This nuclear pull, this nuclear charge, is much stronger for fluorine than it is for lithium. Therefore, that as they're pulling in, those electrons are having to get closer. They don't have as much freedom as let's say lithium would, the electrons in lithium would. This lithium would have a little bit more freedom. The next factor you need to consider is nuclear shielding. And this is more important as you go down a group, down a group, down a family, down the periodic table. When you're going down the periodic table, what you're doing is you are adding energy levels to an atom with each new period, with each new row, you have added energy levels. So you are adding layers between the nucleus, where your protons are, and those valence electrons, the only electrons we care about, the valence electrons, the ones that do chemistry. Okay, you're adding energy levels. So you are basically blocking the view of the protons to see those electrons on the outside, the ones that we care about, those valence electrons. So if you were to look at something like lithium versus potassium, they are both in the very first family, the alkali metals. They both have one valence electron. But the difference between them is the number of energy levels. If you look at lithium, lithium is in the second period, so it's got two energy levels. And here it's its one valence electron. If you look at potassium, potassium has four energy levels. It's got 19 protons, 19 electrons. So it has one valence electron as well. But this one valence electron, these protons have a harder time seeing it because there's all these electrons in the way. So it's going to exert less of a pull on that electron because it's being shielded, nuclear shielding. This valence electron is being shielded from the nucleus, from the protons, from those parents that want to control the electron, from those protons that want to pull those electrons in. So this nuclear shielding is important as you go down the periodic table. Nuclear charge dominates as you go to the right. So as your energy levels are added, your atom is going to become larger. So then you're going to dilute the pull of the nucleus on the valence electrons. You're not going to be able to see it because it's getting further and further away. Just like to make the analogy between a parent and a child, the further the child is from the parent, the less control they have. So when there are toddlers, you keep those electrons close by. You keep your children close by. As you get older, you give them a little more independence. As your child goes to college, they're much, much further away. You don't have as much control over what they're doing. Same thing applies here. These protons are not, because there's more distance between them and those valence electrons, there's going to be less of a control, less of an influence. So as you add energy levels, the atom becomes larger and you're going to dilute that pull of the nucleus on the valence electrons because there's more layers, there's more distance between the valence electrons and the nucleus. Okay? So it's easier, for all that to say is that it's easier to remove valence electrons as energy levels are added. It's easier to remove a valence electron from potassium because it's further away from the nucleus than for lithium. Okay? Easier to remove. That's going to go into ionization energy. We'll talk about that in a little bit. Okay, the last rule you need to, we got rule number 1, nuclear charge. That's as you go across the pull of the electrons. The more protons you have within the same energy level, the more it's going to pull in. Okay, number 2, nuclear shielding. The more energy levels you have, the less influence your nucleus is going to have on those valence electrons. And now the third rule you always need to think about is the octet rule. Remember, the goal of almost every element on the periodic table is to have the same electron configuration as the noble gas that's in their period. Normally that is 8 electrons. That is called the octet rule. So atoms are going to lose electrons, they will gain electrons, or they will share electrons with the overall goal to look like a noble gas, to be dressed like a noble gas. They're still going to be the same atom they were to begin with because they're not changing the number of protons, but they're changing their clothes. They're changing the number of electrons. They're looking different. Okay. As those elements get closer to the noble gases on the periodic table, there's going to be a greater attraction for electrons. They're really, really want to get electrons from wherever they can. Okay, this is going to be important when we get to electronegativity. Okay, So keep those three things in the back of our mind when we're talking about our periodic trends. The first trend we're going to talk about is metallic character. How much of a metal is an atom really? So to remind you what makes a metal, the properties of a metal. Metals are easy to shape. That means they are ductile. You can pull them into thin rods, or you can pound them flat. That means malleable. They can conduct electricity, and they're shiny. So we're trying to figure out which atoms on the periodic table have the most metallic character, act the most like a metal. So if you think of the periodic table, it is always a transition. There are some things that have more metallic character than others. So if you are thinking about your periodic table, if you think about how it's colored, and I will put up a periodic table in a second after we talk about the trend, you want to remember that the majority of your periodic table is a metal. All the transition elements, your rare earth elements on the bottom, and anything to the right of that, to the left of that stair step is a metal. How metallic it is. The top right-hand corner of your periodic table are your nonmetals. So one way of thinking of how metallic something is the further away you are from that non-metal section of the periodic table, the more metallic you are. So what does that mean? Means you go down a period, down a group, your metallic character increases. You go down a table, down the table, you become more metallic. Okay. As you go towards the towards the nonmetals, you're going to become less metallic. So you're going from metals to nonmetals, you're going to become less metallic. The most metallic thing on the periodic table is francium. Bottom left-hand corner of the periodic table. The most non-metallic thing on the periodic table is helium. It's good to keep those extremes in mind. Okay, so here's my periodic table that is colored the way that you should have colored it before. As you notice, the majority of the periodic table is yellow. The reason it's yellow is because there's metals. That's one of the things that you needed to color was your metals. These down here are also metals. Over on the top right-hand corner is your nonmetals. And this is that staircase I talked about, those metalloids. Okay, so I'm going to switch periodic tables because I have it labeled on a different periodic table. Okay, so let's label our metallic character. Okay, so we said the further away you are from the nonmetals, which were over here, the more metallic you are. So the furthest from this top right-hand corner is this bottom left-hand corner. That means as you go down the periodic table, we're looking at this line right here, down the periodic table, your metallic character increases. You become more metallic. As you go down the periodic table, your metallic character increases. Okay? So in other words, if you were to look at potassium versus cesium, you're more metallic as you go down. So cesium would be more metallic than potassium. Okay, and you should be labeling your periodic table with these arrows. Okay, the other thing, the further away you are from your nonmetals, the more metallic you are. So as you go across the periodic table, you become less like a metal. So again, I like drawing my arrows in the direction of increase. So your metallic character increases as you go from right to left, right to left. So chlorine is less metallic than silicon. That's further to the right. So your metallic character increases to the left and down. The most metallic thing you have is francium. The least metallic thing you have is helium. Make sure you label your periodic table. We're going to see all these different arrows. We'll be adding to our periodic table as we go through each of these trends. Okay, the next trend we're going to talk about is atomic radius, and that's the general size of your atom. Specifically, it's the distance from the center of the nucleus to the outermost energy level, the distance from the nucleus to your valence electrons, the only electrons that matter, the distance from from the nucleus to the valence electrons. Generally, our atomic radius, the size of our atom, is going to increase within a family. Within a family. In other words, you're going to increase as you go down, as you add energy levels. And we're going to talk about why in a second. The atomic radius decreases as you go across the periodic table. You're getting smaller as you go across the periodic table because you're adding more positive charge. As you're going down, your nuclear shielding is dominating. As you're going to the right, your nuclear charge is dominating. Okay, let's talk about each of those individually. Well, let's look at what that looks like. All right, first of all, let's talk about individually. As you go across a period, same energy level, you're going to have, like we talked about earlier with nuclear charge, you're going to have 3 protons pulling on 1 electron versus 9 protons pulling 1 electron. The pull is harder. So as you're pulling on those electrons, the whole thing shrinks in because you've got more parents, more adults keeping their eye on those valence electrons, those electrons on the outside. They're pulled in tighter to the nucleus because of the stronger magnetic nuclear pull, that positive pulling on that negative. The more protons in the nucleus, the stronger the electrons are pulled in. If we're talking about the same energy level. As you're going down the periodic table, you're having that nuclear shielding issue where you're adding energy levels. So your atom is getting bigger and bigger and bigger and bigger. So as you're getting bigger, those electrons in the outer shell are getting further away from the nucleus. So that nucleus has less of a pull on those electrons. Okay, so what does that look like in terms of a trend? So if you were to look at the trend, first of all, this is what your atomic radius looks like. As you go to the right, you're getting smaller. As you go down, you're getting bigger. Now, one thing I want you to notice, hydrogen is bigger than helium. Lithium is bigger than beryllium, is bigger than boron, and so on and so forth. Same thing here. But your effect across a period is much smaller than your effect of adding energy levels. So if you add protons, that effect is not as big in terms of the atomic radius than it is adding energy levels. You're going to have a much bigger effect going down than you do going to the right. Okay, another way of remembering your trend for atomic radius is you can think of a snowman. Snowman has the biggest thing on the bottom, smallest thing on the top. So that is what your atomic radius looks like. If you look at the periodic table, there's like a snowman standing up. The smallest thing's on top, the biggest thing is on the bottom. Then somebody comes and kicks your snowman over. So he lays down. So now you're going to have the biggest thing on the left and the head is over to the right. The smallest thing on the periodic table is helium. The largest thing on the periodic table is francium. This trend is the same as the trend for metallic character. So now let's label our periodic table. I already gave you the answer to this one. Okay, so let's label our periodic table. We said let's do the easy one. As you go down the periodic table, you're becoming larger because it's like a snowman. The head's on the top, the snowman's on the bottom. So you go down the periodic table, you're becoming larger because you're adding more energy levels. Therefore, there is less of a pull from the nucleus to those electrons. So you're getting bigger. So as you go down, your atomic radius increases. As you go from right to left, you become larger. Okay, your smallest thing on the periodic table is helium. Your largest is francium. You go from right to left, you become larger. Again, it's like that snowman. You knock that snowman over and it lays down like this. Your smallest thing is to the right, your largest thing is to the left. So if we were to compare things, if we said who was smaller, selenium or bromine, selenium or bromine? Bromine is smaller because it's further to the right. Selenium is larger. If I would say who is smaller, nitrogen or bismuth? Nitrogen is smaller because it's further up. Okay, remember, I'm going to remind you again about that octet rule. The goal of most atoms, with the exception of hydrogen and helium, they need two. Boron and beryllium we'll talk about in next unit. The goal of most atoms is to have an octet or a group of 8 electrons, with the exception of hydrogen and helium, which need 2. And for this unit, we'll assume boron and beryllium need 8 as well. So the goal is to have 8, and they're going to do whatever they can to get 8. They're going to accomplish this either by giving their electrons away or taking them in. If they give away their electrons, they are typically a metal. Metals like to give away their electrons. If they give away their electrons, you have your protons and your electrons are no longer equal. Now you've lost some electrons. So you have more protons than you have electrons. When you have more protons, more positive than the negative, overall you are positive. Okay? Your nonmetals like to take electrons from other atoms. They like to gain electrons. In other words, they have more electrons than protons. So if they have more electrons than protons, they are negatively charged. So atoms that have gained or lost electrons are called ions. Ions. Okay, so what's ions? Ions are atoms that have gained or lost electrons. The number of protons does not equal the number of electrons. And the reason this happens is because they're trying to get an octet. They want 8. They want 8, and they're going to do what they can, whether that be by ditching electrons or gaining electrons from another atom. Okay. When an atom gains an electron, it becomes negatively charged because it has more electrons than protons. More electrons than protons. It's called an anion. An anion is a negatively charged atom. Okay? If an atom loses electrons, it becomes positively charged because it has more protons than electrons. It lost some electrons, so it has more protons than electrons, so it's positively charged, and it is called a cation, not a cation, a cation. And the way you remember that a cation is positively charged, if you look at the word cation, it has a T in it. The T is like a little plus sign. A cation is a plus sign. Okay? So our metals love to be cations. Our nonmetals like to be anions. Okay? When we're talking about the size of an element, we're going to be talking a battle between the protons and the electrons. That's all that's going on. Protons want to control the electrons. Protons, the adults, want to control the children. Children want to get out, go far, and the protons, the parents, want to keep them close. It is that battle between the two, and that's what we're going to be discussing. But we're going to label our charges on our periodic table now before we go any further. Okay, you remember from the previous lessons that we talked about valence electrons. We said that everything in this very first column has one valence electron. We said that everything in this column has 2 valence electrons. 3, 4, 5, 6, 7, 8. Remember, the goal is 8 electrons. We also said the transition elements tend to have 1 or 2 valence electrons. Okay? So you should have labeled that on your periodic table already. 1 valence electron, 2 valence electrons, 3, 4, 5, 6, 7, 8. It should have been labeled already. Those are the numbers that are highlighted. Okay, so remember, we're trying to gain 8 electrons. 8 electrons. So we're going to start over here. Fluorine has 7 valence electrons. 7. It wants 8. So if it were to gain one electron, it would get an 8. It would have 8 electrons. It would form an octet. That is its goal. So it's going to do that. It's going to do that if it can. So fluorine is going to try to get an electron really easily. So if it gains an electron, now you're going to have 9 protons, so a positive 9 charge in the middle, but you gained 1 electron. So instead of having 9 electrons, you have 10. You have a positive 9 in the middle and a minus 10 on the outside. Overall, fluorine's going to have a minus 1 charge. Chlorine also has 7 valence electrons. It's going to want to gain 1, so it's going to have a minus 1 charge. Bromine, minus 1. Iodine, minus 1. So on and so forth. Everything in this row, in group 17, in the halogen group, if it was going to get electrically charged, it's going to get a charge of -1. Your noble gases will never get a charge because they're already perfect. They already have 8. They already have their octet. Okay, oxygen has 6 valence electrons. If it gains 2 electrons, shortest path to an octet is to gain 2 electrons. So if it does that, it would get a charge of a -2. Everything in this column gets a -2. Nitrogen has 5 valence electrons. Its shortest path to an octet is to gain 3 electrons. Everything in this column gets a -3. So you should label that -1, -2, -3. We're going to come back to carbon in a second. Let's go to the other side of the periodic table. We said that everything in this column has 1 valence electron, and they want 8. So sodium has 1 valence electron. It wants 8. So I can either gain 7, and it becomes like argon, has the same electron configuration, or it could lose 1. If it loses 1 electron, it goes from 11 electrons to 10. That is its shortest path. Losing 1 electron is its shortest path to gaining an octet. So I'd prefer to lose 1 electron than to gain. So everything here gets a +1. Everything here gets a +2. Everything here gets a +3. So let's look at the group right here in the middle, carbon. Carbon's shortest path to gaining an octet is either gaining 4, because it's got 4 valence electrons, or it could lose 4. Because of that, it would rather not do either. However, if it were to get a charge, it would be a plus or -4. So make sure you label your periodic table. +1, +2, +3, plus or -4, -3, -2, -1. So now that we've learned about atoms, now that we've learned about ions, let's talk about the cations and the anions. So we're going to start with cations, and in terms of, since we're talking about trends in this unit, we're going to talk about their sizes. Okay, so first of all, a cation is a positive ion, an atom that has lost an electron. So it has more protons than electrons, so it's positive. It has more positive stuff than it has a negative stuff. Okay, it's called a cation, not cation, cation. Okay, so it's got more protons than electrons. So if we were to compare a cation to its parent atom, so the atom that does not have a charge, if you have an atom, generic atom like atom A, if you were to compare it to its cation, something charged, A plus, your cation is going to be smaller than the original atom. Your cation, the thing with the positive charge, is going to be smaller than its original atom. Why is that? Well, we have more protons than electrons. We have more parents or adults controlling protons controlling electrons. More parents or adults controlling the kids. The more adults you have, the more under control those kids are. The more protons you have, the more under control those electrons are, so that the whole atom shrinks in size. So for instance, if you were to compare calcium to calcium 2 plus, which is the charge that calcium likes to get, because it's in the second column, then calcium 2 plus would be smaller than calcium, or calcium would be larger than calcium 2 plus. Because it's that battle between the protons and the electrons. Okay, an anion. An anion is when you have an atom that has a negative charge. In other words, it gained an electron, so it has more electrons, more negative stuff than protons, positive stuff. So if you were to compare the size of an atom to its anion, atom A versus A minus, A minus is bigger than A. Why is that? It's that battle between the protons and the electrons again. Here in A minus, you have more electrons than protons, more kids than children. Because there's not as many adults watching those kids have a little bit more freedom. They can spread out a little bit more. There's not as many protons pulling in on those electrons so they can spread out a little bit more, less of a nuclear charge. So your anion is larger than your parent atom, your original atom. Okay? So to summarize that, your anion A, atom A, its cation is smaller and its anion is bigger. If you were to compare fluorine versus fluorine minus, fluorine by itself, F by itself is smaller than F minus. Okay? So we've already labeled our periodic table, but let's just show it again. We're only labeling the representative elements, the group A elements. Your alkali metals are a +1. Your alkaline earth metals are a +2. Your boron group is a +3. Your carbon group can be a plus or -4, but it doesn't really like doing that, so it's not labeled here. But if it were to get a charge, it would be a plus or a -4. Then you got a -3, -2, -1. No charge for your noble gases because they don't want electrons at all. Okay, so now let's talk about in terms of trends. So your ionic radius is the size of your ion. In other words, it's the measurement of an ion in a crystal lattice. When ions get together with other ions, when a cation gets together with an anion, they pack in what's called a crystal lattice. They're held together by an electrostatic charge due to those charges, and they pack in a crystal lattice. So the ionic radius is that measurement of the ion in that crystal lattice, the size of an ion in a lattice, one ion. Okay, and it's measured in picometers and angstroms. And again, your cations are always smaller than the original atom, and your anions are always larger than the original atom. It is that battle between the protons and the electrons. So now let's talk about the ionic radius on the periodic table. Okay, we've already talked about all that. So if you were to compare, let's say, lithium versus lithium plus, you see that lithium is larger than the cation. Sodium is larger than the cation. Potassium is larger than the cation. Magnesium is larger than its cation. Okay. Now let's compare just the blues. So we're going across the periodic table. If you notice, lithium plus is larger than beryllium 2 plus. It's the same trend you see for your atomic radius. Sodium is larger than magnesium. Sodium plus is larger than magnesium ion. Potassium ion is larger than the calcium ion, and so on and so forth. Now let's look at the negative ones. N3 minus is bigger than O2 minus. Again, it's the same trend we've seen all along. Okay? That brings us to an isoelectronic series. And an isoelectronic series is a series of two or more species, two or more atoms that have identical electron configuration. In other words, the same number of electrons, but a different nuclear charge, a different number of protons. An isoelectronic series has the same number of electrons, but a different number of protons. So for instance, if you were to look at O2 minus, this is the oxygen with 2 extra electrons, fluorine with 1 extra electron, and neon with no extra electrons. Oxygen normally has always has 8 protons. If it is a neutral atom, it has 8 electrons, but it's got a -2 charge. That means it added 2 electrons. So in this case, O2 minus has 10 electrons. Fluorine normally has 9 electrons, but this is not fluorine. This is fluorine with a negative charge. That means it added 1 electron. It has 10 electrons. Neon is a neutral atom. It has 10 protons and 10 electrons. These are isoelectronic to each other. They have the same number of protons, the same number of electrons, but a different number of protons. Remember, your isotopes were the same number of protons, different number of neutrons. Iso means same, but in this case, it's same number of electrons, different number of protons. Okay? And the reason we have these isoelectronic series is because we can talk about them in terms of their sizes. Same number of electrons. Remember, your electrons are the things that determine the size of your atom. They all have the same number of electrons, so you would expect their size to be the same, but there's not. And the reason they're not is because of the number of protons. Remember, those protons are pulling in on the electrons. The more protons you have pulling on the electrons, the smaller you're going to be because they're controlling things a little bit more. Okay, so here's a couple different isoelectronic series. H minus is isoelectronic with helium because hydrogen normally has one electron, but now it's got a minus charge, so it's got two, just like helium. Lithium normally has 3 electrons, but it's got a positive charge. That means it lost an electron, so now it has more protons than electrons. It has 2. Beryllium normally has 4, but it's got a 2 plus charge, so now it has 2 electrons. Those are isoelectronic to each other. We already talked about some of these, but let's continue. We talked about nitrogen, oxygen, fluorine, and neon. Now let's talk about sodium. Sodium normally has 11 electrons, but it's got a +1 charge. It lost 1 electron. When it loses 1 electron, it gets the same electron configuration as neon, so it has 10. Magnesium normally has 12. Now it has 10 because it lost 2. Aluminum normally has 13. It lost 2. It is 3. So for an isoelectronic species, if you were trying to figure out the difference in sizes for these guys right here, the thing that is the most positive, remember your cations are smaller than your parent atom. The thing that is most positive, in other words, has the most the biggest disparity between protons and electrons on the proton side, where protons are winning the battle, the thing that has the most protons is going to be the smallest, and the thing that has the most the thing where the electron is winning the most is going to be the largest. That's your anions. So in other words, for an isoelectronic species, same number of electrons, the larger the nuclear charge pulls harder on the electron. Therefore, the larger the atomic number, the larger the number of protons. The higher the protons, the smaller the atom. Aluminum has 13 protons. That's the smallest of the bunch. Nitrogen has 7 protons. It's the largest of the bunch because your size is determined by your electrons, not your nucleus. Okay, but then you have more protons on something that's positive, you have more protons pulling on those electrons. Okay, so let's talk about our trends, ionic trends. We talked about, just so you kind of see what things look like. So if you're going to look at your group trends for your ionic radii, it's the same trend. It looks the same exact way. We'll label our periodic table in a second. But if you look at lithium, lithium normally has 3 electrons, but lithium plus only has 2. So if you were to draw its Lewis dot, it would look like this. Its Bohr model, it would look like this too. And normally, if this was not with a charge, you would add a 3rd electron on the outside energy level. But you're not going to because you don't have it. You lost it. So the size looks smaller. Sodium normally has 11 protons, 3 energy levels. If you were going to add your electrons, if you're going to add your 11th electron, it would go in this energy level. But you've lost that. So now you've lost one. And so that 11th one disappears, and look, it's smaller. That kind of gives you a visual representation of how it shrinks in size. Okay, so if we were to label our periodic table, you will label exactly like you labeled your atomic radius. So again, your ionic radius is the same as that of your atomic radius. Your atomic radius is right up here. If you look, your ionic radius also decreases as you go left, generally, and increases as you go down, generally, because you're adding electrons. You're adding energy levels as you go down. It is the same trend in this as atomic radius. So your metallic character, your atomic radius, and your ionic radius all have a very similar trend. Okay, the next trend that we're going to talk about is called ionization energy. That is the energy required to remove the outermost electron from an atom. In other words, the energy required to remove a valence electron. Since you are removing a valence electron, You are becoming positive. You're removing an electron. So now you're going to have more protons than electrons because you removed one. So this is the energy required to become a cation, the energy required to remove the outermost electron from an atom. For anything to happen in chemistry, there has to be a motivation. There has to be a reason for things to happen, whether it's a chemical reaction or removing an electron. And anything that happens, just like in life, there has to be some energy expended to do it. But is that cost of energy worth it? Is there a payoff? Okay, just like if you were at home and you're told to clean your room and you're laying on your bed, it's so much easier to lay on your bed. But you get up, you clean your room, you put in that effort to clean your room, but the payoff at the end is worth it. You had to put in energy, but at the end, the payoff's worth it because now you're in a nice clean room and it's easier to think because it's not organized and your parent is on your case. Okay, same thing happens here. There's an energy associated with removing an electron. There's an energy associated with removing an electron. There has to be, these atoms have to expend that energy. Why would they expend that energy? Well, they would expend that energy if there's a payoff. If the payoff, if it's beneficial for an atom to do it, there won't be a ton of energy to overcome. But if it's not beneficial for an atom to do this, then it's going to cost a lot of energy. They have to put a lot of energy into it. So let's look at something like sodium and chlorine. They're both in the same energy level, same period. They have the same number of energy levels, 3. It is much easier to remove this electron in sodium than it is to remove one of chlorine's electrons. Why is that? Well, chlorine has 7 valence electrons. If it removes an electron, it gets further away from achieving an octet, which is its goal. So why would it go from 7 electrons to 6? Why would it move away? It's not going to do that because it's not beneficial. So the atom is going to make it extremely difficult for this to happen, for that electron to get popped off, as opposed to something like sodium. Sodium has 11 electrons. But if it were to remove one electron, it gets an electron configuration similar to that of neon. If it becomes like neon, it gets an octet, right? You lose this electron here, then you have an octet. So you're happy. So your sodium is going to make it not that hard to remove an electron. It's a lot easier to remove this electron on sodium than it is over here. And that makes sense too, because sodium is an alkali metal. Sodium likes to have a positive charge. It likes a +1. Chlorine doesn't want a positive charge. It wants a negative charge. It wants more electrons, not less. Okay? So if we were going to look at the periodic trend for ionization energy, your ionization energy decreases as you move down a group. Remember, your protons are controlling things, right? They're trying to keep their electrons under control. The electrons are ones who want to leave. The protons are pulling in on those electrons. So if you're going down the periodic table, as you're increasing energy levels, so for instance, this guy's lithium versus sodium. Lithium versus sodium. They each have 1 valence electron. It's going to be a lot harder to remove the electron from lithium because it's closer to the nucleus, and that charge can really pull on it. But now here for sodium, it's got an extra energy level, so there's that nuclear shielding we talked about earlier. That's going to make it harder for that nucleus to really control those protons, to control that electron. It is easier to remove an electron when you have more energy levels than an electron when you have less energy levels. So as you go down, the energy required to remove an electron decreases. Energy means the more energy it takes, the harder it is. Okay. So as you go across the periodic table, your ionization energy increases. In other words, it's becoming harder to remove an electron. Why is that? It's because the atoms are trying to fulfill an octet, and if removing an electron goes against their goal of an octet, they're going to make it really, really hard. So lithium versus fluorine, same number of energy levels, but it's going to be a lot easier to remove that lithium electron than it will be that fluorine because lithium wants to get rid of an electron to become like helium, as opposed to fluorine wants to gain an electron. So we're going to label our periodic table now. So let's label our periodic table. Our ionization energy I have on the right side of the periodic table. As you go up the periodic table, it becomes more difficult to remove an electron. Your ionization energy increases as you go up the periodic table. It's opposite to your atomic radius, your ionic radius, and metallic character. As you go to the right, your ionization energy increases. It gets harder to remove an electron. The thing that is the hardest to remove an electron from is helium. The thing that is the easiest to remove an electron from is francium. So if I were to say who's got a higher ionization energy, is it nitrogen or is it fluorine? It's much harder to remove an electron from fluorine because your ionization energy goes this way than it is from nitrogen. This is going to have a higher ionization. Fluorine is going to have a higher ionization energy than nitrogen. If I were to say who's got a higher ionization energy, fluorine or iodine? Fluorine is going to have a higher ionization energy than iodine. The last periodic trend we're going to talk about is electronegativity, and this is probably one of the more important ones here in this class because it talks about reactivity and it talks about how things bond. And in chemistry, that's what we care about is chemical bonds. So electronegativity is the ability of an atom in a bond. So once things are already bonded, chemically bonded together, to pull on the electron. So sometimes atoms pull really, really strongly, and some of them don't pull that strongly. This has to do with how well an atom shares. Sometimes an atom is not a good sharer. They decide that they're going to share electrons, but it's not a good share. So if you look at something like HF, fluorine has 7 valence electrons. Hydrogen has 1. So fluorine needs 1. Hydrogen needs 2. So you would think this is not going to, fluorine, if fluorine takes the electron away from hydrogen, hydrogen doesn't have 2. And if fluorine gives its electron to hydrogen, fluorine's going to get it further away from an octet. So that doesn't work. So what ends up happening is that these atoms decide to form a partnership. They decide to form a bond. And fluorine says, hey, hydrogen, you've got an electron. I like the way that looks. I want to borrow that electron. And in return, you can borrow my electron. So I won't have 8 electrons around me. I won't have an octet 100% of the time. But if I have it some of the time, that's going to be better than none of the time. And then you, hydrogen, you can have the electrons some of the time as well. And so you won't have your 2 electrons that you need 100% of the time, but you'll have it some of the time. So it's beneficial. It benefits both of us. Okay. So electronegativity talks about how well atoms pull those electrons towards them. So the tendency of an atom to attract electrons to itself when chemically combined to another atom. So they come into this agreement, and you would think, okay, that means that fluorine's going to have that 1 electron from hydrogen 50% of the time, and then hydrogen would have fluorine electron 50% of the time. And that's not what happens. Fluorine is not a good sharer. Fluorine likes to pull those electrons towards itself. Fluorine is selfish. Fluorine is the biggest bully on the periodic table. It is not a good share. It will attract electrons towards itself when chemically combined in an atom with another atom. So HF forms a bond. They form this bond. They come into this agreement. And fluorine keeps that 1 electron that they're supposed to be sharing, keeps it 95% of the time. And every so often, we'll throw an electron over at hydrogen, let hydrogen have it for 5% of the time, and then fluorine gets it back. He's not a good sharer. He is very electronegative. It pulls an electron towards itself when chemically combined to another atom. Okay? If you had 2 atoms that are the same, trying to bond, trying to reach this agreement, like if you had 2 fluorines connecting to each other, then they're gonna pull equally on each because it's the same atom. But when the atoms are different, that pull is uneven because each person each atom has a different electronegativity. The most electronegative thing on the periodic table is fluorine, the worst sharer. The least electronegative thing on the periodic table is francium. Okay, so let's talk about why first. So if we're talking about a trend, as you go down a group, I told you francium is the least electronegative. As you go down a group, your electronegativity decreases. You become less electronegative. In other words, you don't have that ability to pull electrons towards you. The reason you can pull electrons towards you to begin with is because you have a positive core, right? You have your protons. Protons attract negative things. So it's really your protons that are trying to pull these electrons from other atoms. Okay. As you get larger and larger and you're adding more and more and more and more energy levels, your outer shell, which is where you have room for electrons, are getting further from that positive thing. So you're having that shielding we talked about earlier. So your protons can't really pull so well. Your electronegativity decreases as you go down because you have a lower attraction for electrons. As you further up, you have less energy shells, so you have more of a higher attraction for electrons. Okay, now let's talk about across the periodic table. Remember, we told you fluorine is the most electronegative, so we're going to be moving to the right. As you move to the right, your electronegativity increases across a period. And this is because the goal of these atoms is to become an octet. So the closer you are to becoming an octet, the more electronegative you are. Okay. The one exception is your noble gases in terms of this trend. Noble gases has no electronegativity. Their electronegativity is zero because they want nothing to do with anybody's electrons at all because they're already perfect. They already have that octet. Okay. So their electronegativity is not important at all. Okay. So if you were to look at your electronegativity, this is what it would look like. You increase as you go across this way, and you're going to increase as you go up to fluorine. And notice that your noble gases are blocked out. So let's label our periodic table. So if you were to label your electronegativity, as you go across the periodic table, your electronegativity increases. Remember, my arrows are drawn towards the area of increase. That's how I like to do it. As you go up the periodic table, your electronegativity increases. Fluorine is your most electronegative. Okay, so what does that mean in terms of noble gases? I said your noble gases have zero electronegativity. So your trend only works if you do one of two things. Pretend that the noble gases aren't there, or more precisely, or more accurately, what you should do is move your electronegativity to the other side of the table. In your mind, move your noble gases to the other side of the periodic table, okay, because they have the lowest electronegativity. So if I were to ask you who is more electronegative, fluorine or nitrogen, you would say fluorine. But if I were to say who is less electronegative, lithium or neon, because we're going to imagine neon moving over here, neon is less electronegative than lithium because it's got your noble gases have zero electronegativity. Okay, so keep that in mind. If I were to say who's more electronegative, tellurium or sulfur, well, less electronegative would be tellurium, more would be sulfur. If I said who's more electronegative, cesium or barium, neither of them are really electronegative. The barium is more electronegative because it's further to the right. But anytime you see a noble gas, remember, you have to imagine on the other side of the table. So that is all I have for you in terms of electronegativity. And that's it. That's all we have for our periodic trends. I'm going to show you one last slide that has all the trends drawn on them. Okay, so here are all the electronegativities that you should have labeled on your periodic table. Here I have the words decrease and increases, so the arrows are all going in one direction. Your metallic character decreases this way and increases as you go down. Atomic radius is the same as metallic and ionic. Your ionization energy, let's just say ionization energy, um, it increases this way and decreases as you go down. And your electronegativity does not include your noble gases. Make sure you have these labeled on your periodic table because you may use that during a test.